Hey, welcome to the podcast.
Thanks for having me.
I've been thinking about chemistry lately and where does it all actually start? Is it atoms, the universe?
I mean, if you really want to go back, it starts with stars, right? Most of the universe was just hydrogen and helium at first.
Oh, wait, so where did everything else come from?
Exploding stars. Supernovae basically scattered carbon, oxygen, iron, all the heavy stuff across space.
No way. So, the iron in my blood is from a star that blew up?
Literally, yes. You're made of stardust. It's not just a cute saying.
That's wild. Okay, so we've got all these elements now. How do we organize them?
The periodic table, right? It groups elements by behavior. Things in the same column act similar because their electrons are arranged the same way.
And chemistry is basically just electrons doing stuff?
Pretty much. The nucleus is there, but it's the electrons that make all the action happen. Bonding, reactions, everything.
Okay, so when atoms join together, you get molecules. But water doesn't act like hydrogen or oxygen at all. How does that work?
It's the magic. Compounds have totally different properties than their parts. Hydrogen burns, oxygen feeds fire, but water puts it out.
Yeah, water's like the least exploding thing ever. But why do atoms even bond in the first place?
Energy. Everything in nature tries to lower its energy. Atoms bond because it's more stable that way.
Okay, so there are different types of bonds, right? Like sharing versus stealing electrons.
Exactly. Ionic bonds are like stealing. One atom takes electrons from another. Covalent is sharing. Metallic is this weird sea of electrons floating around.
And then there's hydrogen bonds, which aren't even real bonds.
They're real, just weaker. But don't underestimate them. They hold DNA together and fold proteins. They're super important in biology.
Huh, so weak but critical. Okay, so what about reactions? Why doesn't wood just randomly catch fire?
Activation energy. You need enough energy to get the reaction started, like a match. Then it keeps going on its own.
And that's where kinetics comes in, like how fast stuff happens.
Yeah, temperature, concentration, surface area, all that affects reaction speed. And catalysts are the real game changers.
Catalysts. They speed things up without getting used up, right?
Exactly. They lower the energy barrier so reactions happen faster. Industry uses them everywhere. Plastics, medicines, you name it.
I read something about organometallic catalysts being like the secret sauce in chemistry.
Oh, yeah. They're amazing. They sit between organic and inorganic chemistry and do things neither can do alone. Super powerful for making complex molecules.
Okay, shifting gears. Phases. Solid, liquid, gas. That's just temperature and pressure, right?
Basically, yeah. And then there's plasma, which is when you rip electrons off atoms and everything is charged.
Wait, plasma like a neon lights?
Yes, and in stars and fusion reactors, it's the fourth state of matter, and it's everywhere in space.
That's so cool. Pause. Speaking of fusion, I heard they need crazy materials that can survive insane conditions.
Material science is huge for that. You need stuff that can handle extreme heat, radiation stress, chemistry, and engineering together.
So making new alloys and ceramics with special properties.
Exactly. It's all about designing materials at the atomic level for specific jobs.
Let's talk laws. Conservation of mass and energy. Nothing's created or destroyed, just moved around.
Right, and that's why you balance chemical equations. Atoms don't disappear, they just rearrange.
And energy conservation ties into whether a reaction will happen or not.
Yeah, thermodynamics. You look at enthalpy and entropy to figure out if a reaction is favorable.
Okay. Redox reactions. I always get confused. If chlorine takes an electron from sodium, what's it called?
Chlorine is reduced because it gains an electron, so it's an oxidizing agent. Sodium loses an electron, so it's the oxidized and is the reducing agent.
That's so backwards. Why is the thing that gets reduced called an oxidizing agent?
I know it trips everyone up. It's named for what it does to the other thing, not itself.
Okay, got it. What about pH? Acids and bases?
Simple version, acids give up hydrogen ions, bases grab them. There are fancier theories, but that covers most stuff.
And equilibrium, that's when a reaction is still happening, but nothing's changing.
Dynamic equilibrium. Forward and reverse reactions balance out, so amounts stay constant, even though molecules are still reacting.
That's everywhere, isn't it? Like freezing and boiling.
Yep. Phase changes, chemical reactions, even metabolism in your body. Equilibrium is fundamental.
Let's talk branches of chemistry. Organic is carbon stuff. Inorganic is everything else.
Pretty much. Organic chemistry is all about carbon-hydrogen bonds and the crazy variety of molecules you can build.
And biochemistry is where chemistry meets biology.
Exactly. Carbs, lipids, proteins, nucleic acids. Those four types of molecules make life work.
It's kind of mind-blowing that, my thoughts right now are just chemistry happening in my brain.
I know. Consciousness is a chemical process. that's both beautiful and kind of unsettling.
Yeah. Well, okay, analytical chemistry, that's the detective work, right?
Yes, figuring out what's in a sample and how much. Chromatography, spectroscopy, mass spec, all the tools for chemical detective work.
And there are old school methods too, like precipitation.
Oh yeah, what chemistry techniques are still useful? Sometimes simple's best.
What about theoretical chemistry? That's all computer simulations now.
A lot of it, yeah. Quantum chemistry, computational methods, and quantum computers are going to revolutionize it.
Wait, quantum computers for chemistry? How does that work?
Simulating molecules properly requires solving quantum equations, which is insanely hard. Quantum computers can do it way faster because they naturally handle quantum behavior.
That could speed up drug discovery and stuff.
Absolutely. Material design, catalysts, pharmaceuticals. Quantum computing could transform all of it.
Going back to catalysts, they're really the backbone of industry, aren't they?
For me, yes. Without catalysts, most industrial chemistry wouldn't be economical. Petrochemicals, polymers, drugs all depend on catalysis.
Okay, quick run. Neon lights are plasma. Batteries are electrochemistry. Chromatography separates mixtures. Am I getting this?
Lassing, spot on. Add spectroscopy for astronomy and medical imaging, and you've covered the major applications.
The source material says something like, chemistry goes from a single atom all the way to living cells. That's a huge range.
It is, and it reminds you that chemistry isn't just lab coats and beakers. It's fire, metallurgy, medicine, everything humans have built.
Okay, last question. What's one thing from all this that blows your mind?
How tiny changes in electron arrangement change everything. Move one double bond in a molecule, and it goes from a perfume to a poison.
Seriously?
Yes! Electrons rule chemistry, and the smallest shifts have massive consequences.
That's incredible. Well, we covered a ton. Stars to cells, bonds to brains. Thanks so much, Len.
This was fun. Thanks for having me.
All right, catch you later.